Awesome. Thank you. Thank you. Thank you for the introduction. And as Angelica said, my name is Vladimir Vivien. Let me go ahead and start my screen share so we can get going. Um, there you go. I want to share the whole desktop. Okay, so I don't have a backup screen, so hopefully you guys can see my screen. And let's go ahead and get started. All right, so as Angelica said, my name is Vladimir Vivien, and today we're going to talk about real-time video capture with Go. So it's a bit of departure from what the previous two speakers were discussing, which is Tiny Go. And truth be told, when I was approached to do this presentation, I thought about doing something in Tiny Go, but I did not have everything I needed to get going with Tiny Go. Because I wanted to do a specific presentation, but I had a problem lingering. So I went ahead and worked on that. And today that's what we're going to talk about. Once again, I've already had my introduction, but I am Vladimir Vivien. I'm a software engineer. I work at VMware currently, but in the cloud native space, but I'm an all-around technologist. I enjoy working in technology, and the stuff we're going to talk about today has nothing to do with my day-to-day work, but it's interesting, and it was a great find. So I dove right in and start playing with it. Okay, so this is what we're going to talk about today. What is it that what's the motivation? What is it we're talking about? We're going to look at video for Linux a little bit. We're going to explore what video for Linux V4L2 is and how it works with Go. And then we're going to look at Go4VL, which is a little project I started to capture everything that I've learned during this exercise. And then we're going to look at a bunch of demos. So I'm going to move fast so I can get to the demos because we have a lot of code to look at, and then the demos. All right, so right off the bat, everything that I'm going to talk about, everything I'm going to discuss, all the source code, all the examples, I have on GitHub. This is the GitHub repository. If you wanted to turn off everything and walk away from the presentation, don't do that. Know that everything I'm going to discuss and talk about is there. And then early this morning, I released this blog post on Medium that pretty much captures everything I'm going to talk about today. So again, it's there for your, these are resources if you want to check them out. All right, so what's the motivation behind this, right? And just like anything else and everything else for most of us in the last couple of years, it had to do with COVID. So basically, I wanted to build a webcam because at one point, if y'all remember, there was no way, it was hard to find a camera, a webcam. And I wanted to find something, but eventually that turned into a hobby. I just wanted to see if it's something that I can actually build, and started to dig around and see what's available. Eventually, I came up on a lot of documentation, a lot of information, but it was a lot. First I had to learn about Linux device drivers. Then I had to figure out what USB video classes are, because there are such a thing. And then USB video class gadgets and how to set them up. Video for Linux API, which is what we're talking about today, and lots and lots and lots of C. So finally, when I realized that it would have been too much for me to learn all this and build something, I was like, okay, for now, what I want to do is figure out how to capture video using the Video for Linux API. And truth be told, throughout the year last year, folks have figured out how to do exactly what I wanted to do with this is it right here. I don't know if you can see it because I don't have, like I said, I don't have a screen. This is the camera. This is the Raspberry Pi Zero. okay, with the HQ camera, with the HQ lens attached to it. But anyway, like I was saying, folks around the web have figured out how to do what I wanted to do, but they figure out how to do it with C. And naturally, as somebody who write a lot of Go, I'm like, hey, can this be done with Go? So before I answer that, let's obviously the answer is yes, but before we get into it, let's see what Video for Linux is all about. So what is Video for Linux, or V4L2, which is the second iteration of Video for Linux? Well, it's part of a large corpus of code that's part of the kernel that has to do with media infrastructure. You can use it for to capture video or to output video, device control, device capabilities, pixel format configuration, because if you're going to capture video or images, you have to tell the device what is it you want to capture and what format, if the device supports it, that you want to use, and a whole lot more that we're definitely not going to cover today, because it is, like I said, it's a large API. But today, what we're going to focus on, as I said earlier, is video capture and whether or not we can do it with Go. So now let's see what Go and Video for Linux look like. So how does Go work with Video for Linux? Well, you have, a couple of options, right? So we know that from Go, you can make CGO, you can use CGO to make calls to a C library and use what's already available. I could have gone that route, right? But also in my research, when I was looking into this, what I found out is everything that's required to make Video for Linux work are system calls. Well, it turns out that Go has those system calls built in. So what are those system calls? Well, you have open and close, which we do that, all the time if you've ever created or opened a file in Go. But we also need a specific system call that is that Video for Linux relies on a lot, which is IO control, and we'll take a look at that. Map and unmap. Now, these two system calls I had never used before, but luckily they are well supported in Go, and they allow you to basically, what they'll allow us to do is map a buffer, a local buffer to our program. Actually, it's the reverse. We're going to map the device's memory into our running program. That's what memory map does, mmap. And then unmap releases that memory. And then select, which is another system call we're going to see. And basically, we're going to use select to so that we can be notified when our device is ready, so we can read the data that we want. Okay. Now, everything else, so beside those system calls, everything else you have to do yourself, right? Including the values, the data types, and functions that you need to talk to the Video for Linux and to make it work properly. Because we're not gonna use an existing C binding or a binding against an existing C library to do it for us. We have the responsibility of creating all the types and everything else that we need, so that we can talk to the Video for Linux library. Luckily, if you've done Go or if you've dabbled with CGO, you know that most Go types map really well to their C counterparts, which is what Video for Linux supports. So once we figure out what we need to and how to map our types, then we can use them and make calls to Video for Linux. Okay. So now here's an example of what I'm talking about. At the top, we see a Go type called request buffers, and we'll see that being used in a minute. And down in the bottom, we see its counterpart in C. And as you can see, you know, besides just the name difference in the types, we can pretty much see how well the Go type and the C type maps, how they map onto each other. All right, so I've blown through really fast about Video for Linux. So now let's do an actual walkthrough. Again, the code that we're going to look at is available on GitHub. So you know, you don't have to pay too close of attention, but if you want to go back and check it out, you're welcome to. Okay, so let me, oops. Yes, we can do better. Let me go to my editor. So hopefully you can see my my VS Code screen. Okay, so now what we're gonna do, just to prove the point that this is doable and it can be done, I'm gonna walk you through how to use Video for Linux directly from Go, and everything that I need to make it work, I'm gonna declare it in this one file. As you can see, looking at the import section of this source code, there's not a whole lot of dependency outside of the sys Unix package. That's the only thing external that we're going to use. Everything else, we're just going to declare ourselves and use it to make it work. Now, every portion in the code, I try to give you a link if you want to go back and look at what the C counterpart looks like. So I put a link there so you can go back and check it out. And the same thing, I've done the same thing in the in the blog post. As you read the blog post, I put links in the code so you can click and go see what the C or where whatever we were using, where it comes from. Okay, so let's go back to the code. The first thing we're going to do is we're going to declare a layout of our commands that we're going to send to the Video for Linux API using IOCTL, or the IO control command. Okay, so that's what we're doing here. Again, if it doesn't make sense, that's okay, but know that, you know, I'm not making any of this stuff up. This is values that we need so that we can craft our commands to the V4 Video for Linux API. So this whole block basically describes how we want to craft our commands, the size. So each command to the IOCTL is a 32-bit value, and different portion in that 32-bit value means different things. So that's what we're doing here. We're laying out that command so we can use it over and over in the rest of this code. All right. And again, if you want to figure out, or if you want to see where that comes from, here's a link right here. You can click on it and it'll take you there. All right. Now, the first thing we're going to do is define a function that takes that layout, and when we give it a set of parameters, it'll come up with a value that Video for Linux understand. So IO enc, or the IO encoding, it does that for us. Again, if you want to know where that comes from, click on that link above. All right, next, we do some wrappers for the IO encoding. One is for when we want to send functions that is just read only. If we send a function, if we make a system call to Video for Linux and we know that it's just going to read only, we're going to send it like this. So these are a convenience function that uses that function for us. And then we have IO encoding just W, which is, again, that's the reverse. So if we do a function call to IOCTL and we expect a value to be written back to us, then we're going to use this. But if we want both read and write, meaning that we send a value to the API or to the device driver, but we also expect the device driver to return back something to us, then that function call will require a read and write. So again, this is a convenience function that calls the IO encoding for us. This 4-character function, we use that in one place, and we use it to encode or to tell the API that we're interested in using when we're setting up our pixel format. We're going to use that function to tell us to tell the Video4Linux API which pixel format we're interested in using, and we'll see that in a minute. Okay, and then here we have the IOCTL, and IOCTL is IO control. It's well known and well defined in the C world. Here we're basically wrapping a system call that does the IO control for us, and this is using the external package, the sys Unix package to do that call for us. So as I said earlier, we're going to use the 4-character encoding to create a value so that we can tell the Video4Linux API which format we want to use. In this instance, we want to use the MJPEG format for our video. All right. Like I said, you saw the you saw the slide earlier. You do have to declare everything because we're not relying on an external package written in C. We're doing everything ourselves. So there's a lot of groundwork we have to cover before we can send our first command. So that's what we're going through. More values that we need, field any, field none. We're going to use that a little bit later. Another set of values we're going to need is to tell what type of functionality we want to use. When we're using the IOCTL command. Here, we want to tell the driver that we're interested in doing video capture. We're not doing video output, nor are we doing video overlay. I can actually delete these 2 lines and my code will still work. All right. Now, the first type that I need is called format, and we're going to use it to send, to tell the IOCTL, to tell Video4Linux API what format we want to use. Now, it takes 2 types. One is called format. And again, I give you all the links here. If you want to go to see, if you want to go in the C code to see what it looks like. Matter of fact, let's do this. Hopefully I'm not breaking anything. There you go. This is, let's make this a little bigger. Yeah. Did I lose it? Yeah, it's too big and I lost it. Hang on one second. There you go. So this is the C format equivalent of what I'm doing in the Go code, right? So we have format and we have pixel format, which map to V4L2 pix format. And these 2 types I'm going to use to set the format that I want my driver to be in once before I start capturing data. And we do that with this function. So I'm going to I declare this function to do that for me. And later on, I should say, down in the code, we'll see how we use all of these functions as we talk about them. So we're going to set the format. We pass it pix format. And now you get to see an actual IOCTL call being made. I'm doing some unsafe pointer magic here. And the only reason why I'm doing that is because if you look at this type right here, there's an embedded union, an embedded C union, union type in this C in the structure. And I'm not going to go into the detail why this works, but I had to go and research how to do embedded union with Go, but it does work given that I tell it that this type had, I give it basically, actually, let me go back here. You see this data type is 200 bytes. It is the largest type in this embedded struct. So just by doing that here, I'm going to tell Go that about the largest member in that struct. And just doing that, Go will automatically figure out how to bring in that embedded union type and cast it to the proper type, which in this case, it is the PIX format, which represents the embedded union type. Anyway, that's all I'm going to say about that. If you're interested, do a search on Go and embedded union. You'll find more of your fair share of information. Okay, now here I'm calling my the functions that we saw earlier, and we're setting up a value, and that value is the actual command that we're going to send to the via IOCTL. We're going to send to the Video4Linux to basically set the format for us. And this is the IOCTL call. This is the file descriptor after we've opened our files, and we'll see that in a minute. And this is the command. So all of the previous functions that we defined is building a value, a 32-bit value for us that tells IOCTL what function or what command that we want to do. And then all of these are basically, the rest of this is basically the parameter to this command. So this command I'm sending to set the pixel format. Let's see, yes. And so we have to tell it how big the struct is so it knows how to read the data. And then if we're gonna receive data back, IOCTL is gonna use that information Video4Linux API was going to use that information to return data back for us. All right, so that was a lot of detail, and the rest of this is pretty much the same thing. So I'm going to go a little faster so we can get to the punchline later. So more types that I need to define, and this one is to tell Video4Linux the different. It's to tell Video4Linux the different type of memory streaming that I want to use when I want to get the information from the device driver. For our use case, we're going to use memory map. And as I mentioned before, memory map allows our application to basically map into the device's memory space directly without doing any kind of memory copying back and forth. So we'll see further down how to do that. And once we have access to that memory mapped area, we can just read that data as if it is part of the application. All right, so here's the next type that we're gonna define: request buffers. This is the type we saw earlier, and this is the function that we're gonna use it with. And request buffer basically asks Video4Linux to set up to allocate buffers for us. All right, so we're going to move on to the next one, buffer info. This is the next type we define. Again, all of this is coming from C. If you want to see what the original C type looks like, you can click on the link and see what it is. So I'm not going to spend too much time on that. So we have two more types: buffer info, buffer service. Excuse me. Buffer service is the type. Again, here we have another embedded union. So buffer service represent that type. We're going to use it to get information later. And then time code is another type that is, where is it? That we're going to need when we're building our our function call to Video4Linux. Now, the next function we're going to define is map buffer. And again, I've already mentioned that what map buffer does. So first, we're going to make a call to the to tell the Video4Linux that we're interested in setting up our buffers. So we're going to ask it we're going to query a buffer. So query buffer basically asks it asks the driver to not only, so earlier we allocated the buffer, but basically now we're going to query the buffer to get those buffers ready for us. And once that's done, we're going to get so we make our IOCTL call here. And when it comes back, the buff type that we pass to the IOCTL will have data that we actually need. So since we ask the driver to get buffers ready for us, it's going to come back with some information. And we're going to use that information to call the mmap so that we can properly set up our memory mapping. And once we do that, we're going to get a buffer that we can use locally in our application to read the data as the video comes up. All right. Now, start streaming does exactly what it does. It tells the driver to get ready to start streaming. Query buffer, yes, I warned you guys this was going to be a lot because we're basically, this whole demonstration is to show you all the steps that are involved if you were to do this yourself, and if you were to try to do it all the time. This is what you would need to do. So queue buffer, once the device gets our buffers ready, we're going to queue it so that later on we can read that. So that's the call to do that. So I'm not going to go into detail. And then we have a dequeue buffer. When the device filled our buffer with data, we're going to use dequeue buffer to let the device know that we're ready to read that data, so that the data can be, so that the driver can go into a mode where we can read that data. So that's what dequeue buffer does. And you can see it's basically the same type of thing. We set up a type, and we use IOCTL to send that command to the driver. And then stop streaming does the opposite of start streaming. We tell the driver, hey, we're done. Go ahead and release your resources. Now, this function is interesting because it doesn't do any IOCTL command directly, or any video for Linux command directly. But what we're going to use it for is to monitor the device, so that when the device get into a read mode, meaning that we can go ahead and read the device, we'll use that as a signaling mechanism so that we can go ahead and read the data from our mapped memory. And that's all this is doing. So this whole thing is doing that for us. All right, finally, we're into main. Hopefully you're still with me. You haven't left the channel, the stream. Okay, so here's where we're using all of this. First, we open the device. Okay, we're just doing an open file. Next, we do a set format. So we saw that function defined earlier, and we're using the pix format type to do that. I'm going to use 640 by 480 width and height. And then the pixel format is the MPEG. You saw that value earlier. That's what we want to use. And then field any, we're going to set that to field. Field, we're going to set that to field none. Okay, first thing we're going to do is do the request buffer, which will allocate those buffers for us. I'm going to do 3 just to have enough time, because this example, basically, I'm using it as a photo snapping example. So I want to make sure I have enough buffers captured by the time I even look up. So I'm doing 3, but I could have done more. I could have done less. Okay. I'm going to map the last buffer. Okay. So we're doing 3, 0, 1, 2. So the last buffer is the buffer I want to map. And that's the data I'm going to get back as a slice of bytes. Okay. Now we're ready to queue our buffer, and we're going to tell the device to go ahead and get our buffer ready for us. Start streaming. So after that point, the device is going to fill up our buffer, and then we're going to tell the device, okay, wait for you to go into in read mode, so I can now read that data. So we wait for it. Once we get past that point, that means the device is ready to be read. Now we dequeue that buffer that we had asked the device to queue for us. And at that point, we can go ahead and read the buffer, the mapped buffer that we set up earlier to grab data from it. So what we're going to do is read that buffer, that slice of bytes, and we're going to copy that slice of bytes into a file. And that's exactly what we're doing in this portion of the code. We create a file called capture.jpg, and we just use regular Go code, regular file operation to write that data. And then after that, we stop streaming. So it's a lot. Let me tell you, I was confused for weeks researching how to use video for Linux. But eventually, yeah, it kind of made sense once I've read tons and tons of blog posts. Anyway, so this is where we are. Let's see if we can make that, if we can make it work. So I'm gonna go, hopefully you're seeing my terminal. I am logged into, so just so you can see what I have a Raspberry Pi, and then that Raspberry Pi is attached to a camera that's sitting above my monitor. It's basically a webcam. Okay, so now I can use the code that I just showed you to go ahead and trigger that camera, turn it on, and capture one frame. And we'll see what that looks like. Okay, so let's get out of this. All right, so it's already, again, I'm logged into the Raspberry Pi, but I have Go installed on Raspberry Pi just in case I want to build something. So I've already built the raw V4L2. So I'm going to go ahead and run the program. All right, so let's run that, and then let me get ready to smile, and then we're gonna grab one frame, like I said. All right, so that frame got grabbed. So let's see. Okay, now we see we have a new file called capture.jpg. So let me go into VNC right now and see if we can see it. Okay, right here. Did it work? Yay, it worked. So I was able to grab one frame. Okay, big deal, right? Now, if this was the whole presentation, I would have been disappointed, but I took it a little bit further, and let's go back to this so we can, all right, let me go back to the presentation real quick. Hopefully you can still see. Can we do better? Yes, we can do better. And through me looking into preparing for this presentation for about a month on the weekends, I started with this project called Go4VL, or Go for Video on Linux. And basically the idea here is to hide all of this that we just talked about, and hide it away from you, and instead expose idiomatic Go types like channels, so you can just ask for a channel and consume the video or whatever you're doing. So now let's look at what that looks like. So we're going to look at two demos. One is capturing multiple images using that, using the project I just showed you. And then the other one is a live webcam that's we're gonna run on the Raspberry Pi, that's gonna stream me as we're talking and push that onto a web browser. All right, let's go back to the code. Okay, so where am I? There we go. So let's do capture. Let's look at this code. Let's use, actually, before I look at this code, let's look at what the V4L2 package does for us, and then we'll come back to the code. So V4L2, I'm not going to go through the whole thing, but I just want to just show you that everything everything we were just looking, when we looked at the raw capture, because the raw capture example, I wanted you to see all of the steps that are involved in getting this thing to work. But this package hides all of that for you, but it does basically the same thing. We have a device type here, and from that device type, you can get pixel format. You can ask, you can open a device here. Actually, let's see, open a device. Okay, we'll get to the questions later. You can open a device. You can get device capability, crop capability, get pixel format. We saw that earlier. Set pixel format. Start the stream. What else we can do? We can do a capture, and with a capture, which we'll use in a few minutes, you can pass it a frame per second to kind of help you out with, so you don't, you can throttle and control how many frames you get in a second. We're not going to go through the code in detail, and then stop stream. But everything that we did earlier in the raw example, all of it's basically the same thing, but it's being hidden from you, and it's captured here. For instance, you could see if I go to the streaming.go, you can see all of the gory detail of what's going on in the back end, all the types, and you probably saw the types, some of the types we saw earlier, but they're declared here, and everything that you need to start to stream is there for you. And again, the magic of abstraction, right? And computing. So everything that you need is abstracted away for you. So all you have to do is come to the use the device type, and the device type ultimately will give you a channel. Let me go back and show it to you right here. When you call capture, you get a channel of bytes, and those bytes are coming from the mapped area of the device, as we saw earlier. All right, so now let's go back and see how we can use this. Okay. All right, let's close this, and let's look at this example, the capture example. All right, capture example. This example is basically the same example as we did before, but instead of just one frame, it captures, I think, 10. Okay, so if we go down here and we look there, now, instead of doing everything that we did before, setting up the types, etc., we're going to use this package that we just looked at earlier. And here we do v4l2.open. It gives us a device. Once we have that device, now we can call set pixel. We pass it the pixel format that we're interested in. Now all we have to do is say start the stream, and I want to buffer 10 frames. So we're going to ask the device driver to talk to the device and allocate 10 frames for us, so we can fill 10 frames at a time. Now, once we have that, I can say I want to start capturing. When we call capture, we pass it a context in case we want to cancel that context before it's time, but we also pass it a frame per second. So here I'm only doing 15 frames per second. Okay. And I'm only laughing because earlier when I was looking at I was playing with this, I'm like, man, it looks a little choppier than, there's a little lag, but I was messing with it and set it to 15 instead of 30. And now it makes sense why my video was a little laggy. But anyway, so once we have that, we grab the 10 frames, and we're gonna loop 10. Actually, what we're going to do is loop 10 times and then stop everything, because this is the frame channel that we're going to get. Once we get the frame channel, we can loop through it, grab 10 frames up to total frames, and then we're done. As we grab each frame, we write that frame to a file called that with the prefix capture underscore JPG and the extension JPG. And for each frame, we write it to the local file system. And then once we're done, we call cancel to make sure we want to cancel the capture sequence, and then we stop the stream. Okay, so let's look at this real quick. See what we get. All right, so I already built it, so we can do capture. So now I'm gonna sit up. It's gonna take a little longer than before because we capture in 10 frames. So I probably have time to wave. Let's see. Yes. Okay. Now we should have captured 10 frames. If I do LSL, you see all these frames. We can look at these frames. I have VNC running still. So let's go back. And all right, so we see those frames here. Let's start with 0. Yeah, let's see. And we see if I step through. So basically, I'm just stepping through by clicking the right arrow is just stepping through each frame for me automatically. So it looks like it's a video, but it's just each frame being shown successively. Okay, so that was that. Now, I took it a bit further. I was like, what else can I do? Well, it turns out I can build something else. Let's do the webcam thing. All right, so I took the, using everything that we just talked about and the API that I created, now I built something else, something that allows me to stream videos from basically that same setup, but push those buffers to a web browser and create a webcam. So let's run it before we look at the code. So I'm gonna start it. All right, now let's go to hopefully you're seeing this. All right, let me reload. Okay, so you could see me. So you should be seeing me in the browser talking about the video, and I'm pointing and I'm moving. So everything that's going on right now is being captured via the Raspberry Pi and being pushed to my web browser. There you go. I made it a little bit bigger, and you can see it's there's a little lag, but it's not too crazy. And you can that's what I was saying earlier. You can adjust your frame per second to control that. And obviously, you should figure out what your webcam supports, because you don't want to overrun your buffers and you start either it'll give up or you start getting even choppier result. Okay, so now let's go back to the code to see how this was done. All right, so now let me go back to the code again. So let's look at, and the other thing I wanted to show before I look at the code, if we go back here, as this is being streamed, you could see that I'm running an old Raspberry Pi, by the way, because I kind of glanced over and I saw a question, what kind of Raspberry Pi I'm running. This is a Raspberry Pi 3, and it's a few years old, and it's not the last 4. But if you look down here, you could see that the cores are really not being taxed. And you could see the memory is staying stable. So, and the streaming is still going on in the background, by the way. So I'm still streaming. You can see everything is going on, but if we go back, you see that, I'm not putting on any hard pressure on the Raspberry Pi doing this. So I just wanted to point that out. Okay, so now let's go back to the code. so we can see how this was done. All right. Where is it? There we go, webcam. All right, so let's go over this really quick. This is the Go file. And let's start here first. So we have a logo. That's the logo you see on the page. But besides the Go code, I have an HTML page, and that is the page that's being served here. That's what you're looking at right here. Okay, so I wanted to point it out right away. All right, let's go back to the Go code. All this is let's go to the main so you can see. All this is basically a web server. It's a web server code that's using the Raspberry Pi to capture the image, and then as I capture each frame, I'm sending those frames down the browser. So let's look at how this is done really quickly. So again, I'm using the V4L2 package, opening a device, getting the device capability. We didn't go over that, but that's one of the things you can do to see if you can, basically, if you can do what you're asking the device to do. In this case, we want the stream, because you may have a device attached and it doesn't support streaming. So you can ask for device capability and then test those capabilities. So let's see. Okay. So next I set the, actually in this instance, all I'm doing is output that capability to the screen. Actually, if you wanted to see, when I started the program here, you can see right here that this is what I outputted with the device info. Okay. All right. So let's go back to the code. All right. So next, we set the pixel format as we discussed earlier. Now, I said I'm going to start my stream, so I'm going to allocate 15 buffers. Okay. And now that I have my 15 buffers, I'm going to start my capturing at FPS. I set FPS up here at 30, but I only did it that up here so I can display it. And if you go back, you can see it says down here, it says go webcam at 30 FPS down at this area here. Okay, that's why I set it as a global. Okay, so going back, now that I have my device set up, oh, the other thing I want to point out, once I call capture, I get my channel. I'm going to set that channel to a global variable so that anytime, at any point, somebody do a HTTP request, they'll be able to tap into that frame, that channel, and then start streaming right away. Okay, that's why I made it global. Okay, I'm pretty sure it's probably a better way of doing this, but right now that works. And this is the first attempt. This is the first iteration of this code, and I was like, I actually did a dance once I got it working properly, but I won't do it today. But anyway, so now I set up two routes.
Excuse me, Vladimir. I apologize. Sorry to interrupt, and I really love this talk. It's amazing stuff, the dance, but we're running a little over, and I want to see if we can move into the next talk because
absolutely. Thank you.
So if you can refer folks to GitHub for the rest of the code. This is great. I mean, maybe we can set up another session afterward. I really want to see this dance and this 15 frame capture, but maybe we can.
No, actually, that was it. That was it. So I was just going over the code that does this. So that's it. And thank you for your time.